Now, one other thing I want to mention about these rectangles. So we're going to come up with another method which is very similar to the disk method, but has one slight change to it, which we'll look into later on. But the thing is, if I am rotating this rectangle around an axis, in order to produce a disk, I need to have this rectangle perpendicular to the axis of rotation. So when we set up the problem, I didn't mention it, but what I did is I drew the rectangle perpendicular to the axis of rotation. And that right there is absolutely a requirement for the disk method. Right? If you draw your rectangle parallel to the axis of rotation, you're not going to get a disk any longer when you draw that out. You'll get a different type of object which you have to treat differently. All right, so we'll explore that later, but for now, just kind of keep this in mind. You don't really get a choice in what type of rectangles you want to use. The method that you're going to use kind of chooses for you. So if you want to use the disk method while rotating around the x-axis, you have to use vertical rectangles. If we're rotating around the y, then you're going to have to use horizontal rectangles. All right, let's take a look at an example that does require that. So this says to use the disk method to find the volume of the solid of revolution generated by rotating the region between the graph of g of y equals y and the y-axis over the interval from 1 to 4 around the y-axis. All right, so as any time, the very first thing we need to do is get a picture of what our region looks like. So we'll start off with a graph, and generally these are very simple graphs to draw. You often don't get very difficult functions to work with, just something that gives you an idea of what's happening. All right, I'm integrating around 1 to 4, so let me do like 1, 2, 3, 4, 5. I'll do the same on here, 2, 3, 4, 5. That should be fine. All right, so I have the graph g of y equals y. So this right here is effectively x equals y, which is just a line like this. All right, so there's my g of y. All right, we're bounded with the y-axis. So the y-axis is, of course, x equals 0. And the interval 1 to 4, so that's going to be on the y. So this would be y equals 1 to y equals 4. All right, and the reason that I know this is an interval for y is because I'm using a function of y. So the domain is going to be based off of the variable provided. All right, so rotating around the y-axis this time. Okay, so we have our region. All right, it's the region trapped between all these parts. And in order to rotate this region around the y-axis, as I said before, I have to use a horizontal rectangle here. I don't really get a choice in the matter, because if I used a vertical rectangle, what would happen is I would get a different kind of shape when I rotate that around the axis. So I have to use a vertical rectangle. No way around it. Okay, so let's take a look at our formula then. So the formula doesn't change much. It's just now the integral from a to b, pi times our function radius squared, but now in terms of y, and we're integrating dy because we have a horizontal rectangle. Okay, so we just need to figure out what the radius of this disk is at any point in time. So this radius function is just going to be defined by the function g. It's just y, just the value y. So that's pretty straightforward. So this is going to integrate, and remember here, since this is the variable y, these bounds of integration are functions of y. So we integrate on the y-axis from 1 to 4. So 1 to 4 on the y, and then it's pi times the function y squared dy. And this honestly will probably take as much time to evaluate using fn int as not, but I'll go ahead and use it here just so I don't make an arithmetic error. So let's try it out here. Oops, I thought I hit math there. 9. All right, integrating from 1 to 4, and I'm leaving the constant pi out. I can use x or y at this point. It doesn't really make a whole lot of difference. It doesn't have any meaning at this point once the variables are done and matched. And it's just easier to type x's into the calculator. All right, so this integral then results in the value 21, and I should state that that came from fn int, so that my final answer here is 21 pi. Find the volume of the solid formed by rotating the region bounded by the curves y equals x squared, x equals 0, y equals 4, about the line y equals 4. All right. So first off, we really need to see a picture of what it is we're being asked to do here. So let's just start off getting a graph, and let's see. Looks like everything will be in quadrant 1, because one curve here is x equals 0. That's easy enough there. Then y equals 4. Let's see, 1, 2, 3, 4, 5. That should be good. And then y equals 4, of course, would be a horizontal line right here. And y equals x squared. I think what I'm going to do, I'm going to extend, I'm going to make the units along the x a little bit wider. Just because square functions rapidly increase, and I want to be able to see my region nicely here. All right, so 1, 1 would certainly be a point on x squared. 2, 4 would it be as well, and that's actually the intersection, so I'm going to go ahead and label that. Okay, so there is y equals x squared. All right, now we can very easily see the region that is bounded here. So that is in between all 3 of these curves. Go ahead and just highlight that. And the neat thing here is that we want to rotate about the line y equals 4. So this line right here is actually our rotation axis instead of the x-axis or the y-axis, which is different because the x or the y-axis has sort of been defining the bottom of our rectangle every time. And now that's not going to be the case here. So let's see what happens. All right, I think we can work through this. Now I have a general rectangle here drawn in, and here's what's interesting. I can clearly see a top of the rectangle and a bottom of the rectangle. But when we set this up, we need to be really careful about this because remember, this rectangle is really representing a radius. All right, and the radius needs to make sure it's always positive. We always want to have a radius as a positive value. So with respect to the axis we're rotating around, this point on the bottom of the rectangle is actually the furthest point away from the axis. And the point that's furthest away is sort of like, the top value when we're subtracting to find like a vertical distance, for instance. So here's what I'm saying. So the bottom part of this rectangle is always defined by the function y equals x squared. The top is always defined by the function y equals 4. But when I go to get the radius of rotation here, it's going to be the point that's furthest away from the rotational axis, which would be y equals x squared, minus the point on the axis in this case, which probably looks a little bit off, but I want you to be thinking about that. It actually doesn't make a whole lot of difference here in the disk method. And the reason why is when we go to set up our volume, of course it's pi times an integral from a to b of our function defining the radius of rotation squared, and we've chosen dx. All right, we had to do dx because we're rotating around a horizontal axis, so we have to be perpendicular to that to use a disk method. All right, so now, since that's dx, this is r of x. But if you'll notice, everything inside there gets squared. So really, it doesn't matter a whole bunch at this point. Like if I said r of x was 4 minus x squared, or if I said r of x was x squared minus 4. When I plug it into this integral, I'm going to square that thing. So it becomes 4 minus x squared quantity squared, or x squared minus 4 quantity squared, which is going to result in the same answer. And you can see it by FOIL. So this would be the square of the first plus 2 times the first times the second plus the square of the second. Same thing here. Square of the first plus 2 times the first times the second plus the square of the second. It's the same value either way. And it's just like if you're squaring negative 2 versus squaring positive 2. Anytime you put a sign in on a number you're squaring, it just disappears through the act of squaring. So same thing happens here. Now that's not going to always be the case. When we go into the next method that we're going to learn, that really is kind of a point of importance there. But I think we'll get a little bit more knowledge as to what's going on here to be able to resolve that issue a little easier. But just be thinking about it for now. All right, so when we set this up, it would be pi times the integral. We're integrating on the x-axis, so that's going from x equals 0 to this line at x equals 2. The function here is x squared minus 4 quantity squared dx, and then we'll use fn to come up with our answer. Okay, so let's see. Math 9, going from 0 to 2, and here I need to be careful. I need an inner set of parentheses, so x squared minus 4 quantity squared dx, and that gives me this value, which I can change into a fraction of 256 over 15. So this is going to be 256 pi over 15. And there we have it.